thank to all of them. The Hive Think Tank events are brought to you by The Hive. What The Hive is, more from TM Ravi, founder of The Hive and managing director.
Thank you, Sasha. Welcome. How many of you are here for the first time? Wow, that's a lot of new people. Good. Hey, guys, can I request you to come sit down so we don't have multiple side conversations? So it's my great pleasure to sort of welcome you all here. And so the Hive is a venture fund that funds data and machine learning and AI kind of based companies kind of in those areas. So if you see, one of the key areas for us is computer vision, and sort of the talk today. We have a number of startups in our portfolio. I just want to highlight two of them. Neva basically uses AI to kind of develop a cognitive intelligence engine to automate customer support and customer service. They're hiring a bunch of people, so if you're interested, reach out to us. Sensify is an IoT security company that leverages blockchain, also hiring people. If you're going to be on Twitter, please use the hashtag HiveData so we can be part of your conversation. And so with that, so first I'd like to thank SAP, our good friends here, for hosting us tonight. And with that, I'd like to have Yaad Oren, who is VP of Platform and Technology Strategy, to say a few words.
Hello everyone. Okay, thank you, Sasha. So, hello everyone and welcome to the Hive event about deep visual understanding. My name is Yaad Oren. I am from SAP Corporate Strategy Group. I am leading the platform and technology team, and together with the leadership team of SAP, we are shaping the strategy for technology and platform topics. One of them is machine vision and the greater concept of machine learning. I'm a great Hive fan myself, so I'm very excited to be here. Previously to my time in corporate strategy, I was 10 years in the engineering team in SAP, and I'm very passionate about new technologies, and machine vision is one of my favorites. So in the very limited time that I have, I would like to cover 2 points. First of all is what SAP perception regarding machine vision, and the second one is, okay, then what are we doing with it? So first and foremost, SAP perceives machine vision as part of the overall machine learning strategy that we have. It's very important for us to offer a comprehensive machine learning framework for our customers. If you ask me, okay, Yaad, why SAP invests so heavily in machine learning, I would like to quote our CEO, Bill McDermott. For those of you who followed the keynote from last Sapphire, he talked a lot about intelligent business application. And we would like to provide intelligent business application to leverage capabilities like machine vision and machine learning as a whole, because we strongly believe that in 3 to 5 years, machine learning will disrupt the business environment and will create a new IT reality for our customer. So we're going to discuss, this is a bigger exercise than machine vision themselves. We're talking about elimination of business workflows to deeper insight into data, and this will create, like I say, a new reality for our 300,000 customers. So we, as the leading vendor for enterprise application, are obligated to provide them the right framework to kind of be successful with this journey. And machine vision is a very important pillar in the framework that we would like to offer our customers. We will see that machine vision, I will give you an example in a moment, is not only important for being relevant in the new age where artificial intelligence and machine learning is pervasive, but it's also a great lever for new business models and actually make your company run much better. So if we're going to talk specifically about what SAP is doing in machine vision, we can say that we are focusing on 4 domains. The first one is we are working on providing machine vision business application. And here, if I mention Sapphire, we showcase their application. You can find it also online, like brand logo detection, where you can stream a video and then a company can monitor the brand exposure. And think about how important it is for like a marketing manager, for example. I can quantify and measure how much brand exposure do I have and provide better campaigns to generate better leads and really optimize my sales funnel. On the other hand, I can also monitor brand valuation. If someone is unauthorized to use the brand, I can track this as well. So those kind of application, and of course I'm very limited in time, going to create a new reality and new business model opportunities for our customers. The second things, which is very important, are platform services. SAP is not aiming to provide the entire applications that will cover the entire spectrum of our customer needs. So we would like to simplify dramatically working with machine vision for those customers. As some of you might know, we have one of the leading platforms in the market called HANA and HANA Cloud Platform. We do have a variety of machine learning services, then from text analytics to NLP. We do not have yet a comprehensive machine learning services like we're seeing in many startups in the value, but we would like to offer them, and the goal is to simplify working with machine vision for our customers. In our customers, in the enterprise IT, not all of our customers took Professor Malik course, I think is CS280 in Berkeley about machine vision, and we would like definitely to reduce the barrier to integrate with the machine vision capabilities and allow them to customize applications they are getting from SAP, and even more importantly, to create their own use case and then leverage machine vision to differentiate them from competition. So platform services is something very important that we are looking into as well. But the most important part and one of SAP's greatest assets is our customer base. We have 300,000 customers, and we really like to co-innovate from them for two reasons. First of all, it's the best way to learn what really moves the needle in the industry. And we are working with leading brands in the world on scenario like shelf replenishment. So if I'm a retailer, I can monitor my shelves and see if I'm out of stock of certain product, and then immediately replenish it from the warehouse. If I'm a manufacturing factory, I can generate an MRP, a planning from intent from manufacturing, and so forth. Those are kind of use cases that we are listening from customer. So the first point was it's great for us to learn what are the use cases that are going to disrupt the business environment, but also as a strategy guy, it's very important for us to corroborate the need and how machine vision is really something that can be meaningful. Because if we're going to tell it like it is, a lot of the innovation we are looking and around us is not always living in the ivory towers of academia and research and really do impact on the industry. But working with customer, getting bottom-up requests, we are really seeing how customers recognize the value of machine vision, and we are pretty sure that this will be a dramatic component in the new IT reality. And in the last point that I would like to talk about is our partner ecosystem. SAP has thousands and thousands of partners, and they are providing different innovation from different walks of life. We can see a lot of complementary solutions. The one I find the most interesting are the one which are kind of orthogonal and leverage machine vision for a new scenario, like companies like Vuzix who provide wearable devices, provide augmented reality solution on top of SAP backend, like for maintenance, so field technician can have part replaces using augmented reality that recognize the physical object and kind of put on it an augmented reality solution. So those are partner solution, example for a partner that leverage their computer vision capabilities on top of SAP backend. So with this very short introduction, I wanted to cover 2 points. First of all is how SAP perceives machine vision as an important part in our journey to provide comprehensive machine learning from the deep understanding that intelligent business application that leverage AI, leverage machine learning, going to be the new standard 5 years from now will be very important for businesses to not only to survive the digital age, but create new business opportunities. And the second one, I want to quickly share with you the 4 main domains we are looking into. For further information, first of all, feel free to contact me. I will be here, and also I will be happy to hear from you what you think. And also online, you can look for a website like SAP Innovation Center Network, which is the development unit that gather the machine vision efforts at the moment. And also stay tuned for TechEd. This is our annual technical conference where we're going to have some announcement on machine vision, and I just don't want to spill the beans right now. So a lot of content available online. And with that, I would like to bring it back to Ravi and to Professor Malik.
It's my great honor and pleasure. It's my great honor and pleasure to have here today Professor Jitendra Malik. He sort of covers a lot of bases. How many people here went to Stanford? Berkeley? IIT Kanpur? All right, thank you for coming.
Brazil. Just saying.
And I'd like to thank my friend Vas Madakar for helping make this happen. So Professor Malik is the author, the Trade Professor of Computer Science in the EECS department at Berkeley. He has received a huge number of awards and recognition. I'm not going to go through all of them, but he was the what's the thing called when you're the top student in IIT? The top whatever graduating student in IIT in IIT Kanpur in 1980. He was Presidential Young Investigator Award in 1989. Very importantly, he was awarded the Long-Higgins Prize twice in 2007 and 2008. He's fellow of the IEEE, member of the National Academy of Engineering, fellow of the American Academy of Arts and Sciences, and in 2015 was elected to the National Academy of Sciences. We are excited to sort of have him here today. This is going to be a series of talks over the next 6 months on topics related to computer vision and underlying technologies and use cases related to computer vision. He'll give us a talk, and if you can kind of hold your questions till the end, but we promise to have a Q&A session after that. So with that, please join me in welcoming Professor Malik.
Thank you very much. Thank you for the invitation and the kind introduction. So I'm going to take you through some general rambling journey on where computer vision and AI are today and where they should be going. So it's really as much about the present and as it is about the future. So we live in a time when deep learning is one of the hottest topics around, machine vision is important, AI is important, etc., etc. I drive on 101 and I see signs which say machine learning for something. This is good, I like it. I have been in this field for 30 years. I used to teach classes which used to have 20 students and now they have 500. So it's come a long way. So I want to always start by trying to pour cold water, okay? So this is an article in the 1958 New York Times. This is, I don't expect you to read it now, but it's a piece on Rosenblatt. Now, for those of you who may not know, Rosenblatt is kind of the original inventor of neural networks. The perceptron was invented by him back in the late 50s, okay? And what we have now is the third coming of neural networks. The first one was with Rosenblatt in the late 50s and early 60s. It kind of died off with Minsky and Papert. The second coming was in the mid-80s with backpropagation and Hinton, Senowski, etc. And then there is the third coming, which is starting 2010 or so, where there was this good application in speech, and then later in 2013 something with vision. Okay, this article is notable for its hubris, because Rosenblatt at that point, this is 1957, right? So you have to think about what was the computing power available there. So they were able to process like maybe 10 units or something like that. And they were able to distinguish between lines which were oriented like this versus lines that were oriented like that. But Rosenblatt went on to say there is something about later perceptrons will be able to recognize people and call out their names and instantly translate speech in one language to speech or writing in another language it was predicted. Mr. Rosenblatt said in principle it would be possible to build brains that could reproduce themselves on an assembly line and which would be conscious of their existence. Okay, and then here is the part which I find really funny. In today's demonstration, the 704 was fed two cards, one with squares marked on the left side and the other with squares on the right side. In the first 50 trials, the machine couldn't distinguish between them, and then after it could. So all they had was, can I tell whether it's on the left or the right? But yet he did not go easy on his expectations of the future. So we always have to wonder what we can do. Actually, some of these things we now can do, right? Recognizing people, calling out their names, translating speech. I mean, some of this has come by. So the first thing I want to point out is, or ask, try to answer the question, why is it that we can do these things now? What could we do? Why could we do this 60 years ago? Okay, so very basic argument, and this is from Hans Moravec in the mid-90s. He tried to make a calculation. Can you hear me in the back, by the way? Is it clear? Yeah. He made a calculation of what the computing power was of the human brain and of the computers of the time. So you have to make some assumptions about what, so neurons are slow devices, but you have a lot more of them and so forth. So he made, and based on extrapolation from Moore's law, right, that's shown here in this slide, you can try to say at what point would the computing power of your desktop machine be the same as the human brain. And he got a number like 2025. Okay? Now if you move back 10 years, so that's 2015, that's where we are now. Okay, but now you can put 100 machines together. That's perfectly okay. So we now are at a time when you have the computing power of the human brain available for easy access. It just happened. For me as a computer vision and an AI and a machine learning researcher, I didn't have to do anything. Somebody else did the job. Okay, but we are benefiting from it. And that's a very, very big thing. This is really, I have worked in this field for 30 years. And I worked in it at a time when, obviously every 5 years if there's a gain of factor of 10, run Moore's law backwards. So when I started in the field, computing power was 1,000,000 times less. Right? So what we had to do if we were in this field was that we had to cut corners, we had to come up with simplifications. It was chutzpah on our part to want to work on this problem at that time. And we did, and we got a lot of insight from that. But really, the time when we could try to make it work for real was when computing power was available, which is just about now. Now we are bound less by computation and more by a shortage in our ideas. Earlier we were really bound by computation. This is kind of the transition point, 2015. It's not a surprise that this is when it happened. I have been using this slide and giving talks on this from like 20 years ago. And this is the time I expected it to happen, and it has happened. Okay? Okay, so now I'll go big picture. So next, vision is not by itself. Vision is part of intelligence, embodied cognition, if you will. I think of vision, perception, motor control, and language. These are somehow all interrelated, and these are all essential components of intelligence. And it's helpful to think about the ontogeny of intelligence, right? When did intelligence start? Well, when did animals start? Animals are roughly from the Cambrian era, something like 500, 600 million years ago in evolution, when you have these multicellular animals which can move about. So, perception arises simultaneously with locomotion. That's very important. the benefits of perception or vision are to an animal only if the animal can move. If plants or trees, if trees, redwood trees had vision, they might be able to discuss the scenery around them, but it would confer no evolutionary advantage on them. For an animal, because it can move about, it can find food in different places. That's the advantage of being able to move around. Then it can avoid becoming food. For that also vision is important. So it's really the vision coupled with locomotion, coupled with action. There's a great example in biology of this creature called the sea squirt. And this is, it has different stages of its life cycle. There are times when it is moves about, and then later on in life it becomes sessile. It's parked on some rock like a plant. And at that point what it does is it cannot move around, so there is no value to vision. In fact, there is no value in the brain. So it sort of digests it metabolizes the brain, because why use up, see, the human brain uses up a third of our energy. Why waste your energy that way? Just use it up because you have no value to be gained from it. In fact, the usual saying is that this is what tenure does. Once you have a tenured professor, you have no use for a brain because you are stationary. Okay, so you have perception and action as of 600 million years ago. But further developments, continue down the evolutionary line. I'm not going to give you that detailed a lecture. The hand comes into play in the hominid line when we have the early development of primates into the hominids, the line which led to humans. And the hand came, so there's very clear data. What developed first? Was it the hand or the brain? It's really the hand. And the development of the hand led to the development of the brain. Once you became bipedal, once our ancestors came down from the trees into the savanna, then the hands were free, there was an advantage. Manipulation gave you ability to do certain things, and then an extra brain size was beneficial. It's interesting, I found this quote from this Greek philosopher from about 500 BC, who says that it is because of his being armed with hands that man is the most intelligent of animals. The hand comes first, and the fossil record tells you the development of hands and the development of brain size. Brain size comes later. And then something like 100,000 years ago you have language. Okay, so what's the big story? The big story is that in ontogeny, in phylogeny, there is a sort of this order where vision and locomotion came first, then manipulation, then language. If you look at children, the same thing happens, right? They are born with some vision, rudimentary vision. Their vision is very blurred, but it gets better over time. The locomotion comes a bit later, right? And manipulation, fine motor control is even harder, and language. Today where we are, and if you think about now, forget all this biology, let's talk about machine vision, machine locomotion, AI. Which of these areas is the most successful? Which area have we had the closest to human capabilities? Vision? No. Language there is no proper understanding yet. We can do translation, but we really don't understand language yet. The systems today do not understand language. We can do vision, and you can do locomotion, and if you put the two together, what do you get? Self-driving cars. So why do you have self-driving cars now? Because these capabilities are now there, right? Okay. Manipulation, we are nowhere near human capabilities. This guy, this hand, is an amazing device. The robot hands are these stupid two-finger grippers. They can do this, right? They can do this. This is not the hand. The hand, the degrees of the freedom, tactile sensing, force feedback. It's just a beautiful, amazing device. In vision, we are lucky. The camera and the eye are comparable in terms of the basic sensing capability. The number of pixels we have. 30 years ago when I started in the field, this was not true. But today, the cameras are as good as the retina, or even better. They'll get even better, but may not matter. But The hand is not like this. Locomotion, if you consider wheel locomotion, it's as good. In fact, even better, because you can, obviously cars can go much faster than humans. So, the evolutionary order has been replicated in the development of machines. Okay, so now what I'll do is I'll just continue rambling, right? I'll give you little comments on each of these fields. So vision is the most successful of these fields. Okay, and here's an example of success. I picked a paper from last year. This is on object detection. And if you look at this paper, it is very impressive. This is the result of many years of, I'm not getting into the details of how we got there. But the input is an image, and the output are these let's see if I can do this pointer, but maybe it doesn't matter. So you have these boxes. Can you read the boxes? And they have some labels like person, book, knife, wine glass, even the dining table can be found with some number which corresponds to the score. So this is very, very impressive. So about 15, 20 years ago, we developed the capability to detect faces. About 10, 15. So and that was a big deal. You started to put it in cell phones and everyone was impressed. But now we have the capability to, at a reasonably high accuracy, do this for any object. And since it's a machine learning approach, we can, if we have enough training data, we can do this for anything. How did we get there? So a little history lecture. So the core idea of this style of work, which is this neural network line, which, as I said, we are right now in the third round of that. Human and Wiesel, these were two neuroscientists who got a Nobel Prize for this work. The work was in the around 1960. They got a Nobel Prize in 81. And what they did was they found cells first in the cat and then in the monkey, which corresponded to, which were orientation sensitive. So there were neurons which respond to vertical edges, other neurons which respond to 45-degree edges, others to horizontal edges, and so on. And this capability is there in humans. It's right here. It's in the cortex at the back, the visual cortex. Vision is a big part of the brain. It's something like 30% of the human brain. For monkeys, it might be 50%. And so there is this capability. And then you have a hierarchy of this. So you have, at an early stage, cells which respond to edges at a specific location. Later on, they'll respond to an edge of the same orientation, but they'll be somewhat tolerant of position. As you go higher up, they are responding to more and more complex stimuli. For example, they might respond to faces, but they'll be less and less sensitive to position. So Hummel and Wiesel had sort of a crude, not a mathematical model with this hierarchy of computations. Someone called Fukushima back in 1980, okay, he proposed, he just took the ideas of Hummel and Wiesel based on what they had learned from neuroscience and made a neural network model with multiple layers. And the layers were simple cells, complex cells. So these are terms from Hummel and Wiesel. Simple cells fire at an edge, at a particular orientation, at a particular position, and complex cells will not care. They are sort of phase invariant. You can shift it about a bit. And then as you add later layers, you get more and more complexity of the stimulus to which they respond. And it's shown in this is a 1980 paper. And then he said, okay, this might be the architecture. This is what is a plausible architecture for the visual cortex. Let's use it for recognizing digits. So this was his idea that he didn't have a good training algorithm for this. He didn't know how to put the weights in this network. Now in the 80s, backpropagation was invented, or rather rediscovered. There are a couple of times it was rediscovered. And so this is, once that was done, Jan LeCun took the Fukushima's neocognitron idea and just decided, okay, let's apply backpropagation, which was a simple gradient descent procedure for tweaking the weights of this network. And let's do it with that. and he showed that it could do reasonably well on digit recognition. So that was the second neural network revolution in the mid to late 80s, where neural networks were shown for many applications, and they were very effective. Then what happened in the 90s was that basically there were other machine learning techniques that were developed, which worked about as well as neural networks, but which were much easier to understand. So support vector machines is an example of those kinds. Decision trees is another technique. And that's why neural networks sort of fell out of favor. It's not that they stopped working well. I mean, they worked reasonably well. It's just that there was an art in making them work, and there were other techniques which were much easier to use and much better understood. So that's why neural networks went out of favor in the 90s and early 2000s. Now, what's happening in the meantime? In the meantime, the computing world, computers are getting faster, right? That's a very important background process for all this. The other thing that had happened was that the internet was there, and lots of people were putting up images on the web. So the number of images that people were putting up on the web was going up. So people say there are a trillion photos and so forth, right? Okay. Now, what people in the computer vision community started to do was to say, let's take these collections of images that we can get easily from the web, and let's annotate them, let's mark them as this is an image of a dog, this is an image of a cat, this is an image of a zebra, and so forth. So they started to mark up these images. In fact, the web made that possible as well, because there's Amazon Mechanical Turk, by which you could do crowdsourcing. So what I'm trying to do is to take you through a sort of a socio-historical perspective on our achievements now. These achievements now are not due to a single breakthrough idea. It's really the force of technology moving along multiple paths. So now we have these big annotated data sets. So, but till 2000, around 2010, some of the speech work had shown that neural networks were pretty effective. They beat out hidden Markov models, which was a previous technology. But in vision, it was not the case. I mean, these were techniques, but the dominant paradigm in the field was not so. In fact, in 2000, I think 2012 or 13, one of these, I got a phone call from Jeff Hinton. Jeff Hinton, if you don't know, he's considered the father of deep learning. So I was in my office, I picked up the phone and he said, "Hi Jitendra, this is Jeff." So I said, "Hello." He said, I hear that you are a critic of deep learning." Okay, that is a pretty bold opening sentence for, I expected a social call, but no. So I said, "Yes, okay, this is just a device to, get some time while I'm trying to figure out what to say." So, and he said, "Is that?" I said, "Yes." So he said, because he had heard that at some conference I criticized deep learning. So he said, "Bye." So I said, "Because you haven't proved your case." I mean, for deep learning, people had been propagandizing from the 2008, 9, 10, 11, 12, 13, but it was like a small group who were, at that time, it felt from the outside more like a little religious cult of people who internally all believe in a certain set of beliefs, but the wider world says, okay, let them continue with them. So he said, "Okay, what would," so I said, "Yeah, because you haven't proved it." So he said, "Oh, but we have results on MNIST and CIFA." I said, "But those are not serious, those are not real world data sets." So he said, "What would convince you?" So I said, "Okay, there is a data set called Pascal, which is what the computer vision community regards as important for object detection. If you get good results on that, I'll be impressed." So he said, then he called me back the next day. He said, "We can't do Pascal because Pascal has only 20,000 images, and the kinds of neural networks that I believe are important are ones with many layers, and these have many parameters, and we won't be able to train them. What do you think of ImageNet?" So ImageNet is has a million images, and it has a simpler task. It was collected by Fei Li, who is currently at Stanford. And he said, would that be impressive? So I said, sure, that's a deal. So he said, okay, I'll call you back in 6 months. And then at the meanwhile, NVIDIA had developed GPUs. So he gave his student Alex Krzyzewski GPUs and said, okay, take this GPU, see if you can make a neural network get good classification results on the image net. And that guy's name was Alex Krzyzewski, so the network is called AlexNet. And that came out with results which were significantly better than conventional computer vision techniques. It was presented at the main computer vision conference, and as they say, the rest is history. But this is kind of the background. It's really the ideas of neural networks go back quite a bit. They are inspired from biology, but why they are successful now is the result of computing, data, labeling, which are due to technological factors which were operating simultaneously. I am a researcher and a scientist. I would really like everything to be based on clever ideas thought up by professors like me. But in fact, it's not. It's really the forces of technological change, which are, there is a giant sea in which we swim. A giant river is probably a better metaphor. Okay, so I am a scientist. I was critical of deep networks, but once they were shown to be good, I mean, I had everything else in place for trying to exploit this development every day. So our group showed, for example, that you could do more than whole image classification. You could recognize particular objects. So this is something called RCNN. So 2014 we had this, essentially 2 papers came out, one from us, one at Berkeley, one from folks at Google. They showed that you could do object detection. Then there was something called fast RCNN. Then people started to make these networks deeper and deeper. So the paper, the people got it up to like 100 layers. And that's the setup in which where we are today. So object detection and object recognition is largely a solved problem, which is very impressive. And it's the result of fairly simple architectures, but the availability of huge amounts of data and label data and computing. So, okay, so now I'll take so this is kind of the solved part, but this is boring, right? Anything which is solved is to you guys interesting because you can make money off it. To me, it becomes uninteresting. Okay, I'm doomed to work only on problems which I cannot solve. Okay, so let me turn to that. So I actually will go on a little bit more about solved problems. So what are the key problems in computer vision? So I like to call them the 3 R's of vision. So there's recognition, which is labeling objects as chairs, dogs, cats, so forth. There's reconstruction, which is about 3D geometry, and reorganization, which is about segmentation and grouping, finding what group of pixels belong together. And I've argued for some time that these are all coupled problems. Instead of classically we worked on them separately in different silos, information should flow back and forth between them. And this is how we do things now. I think earlier we used to argue about it, but it's now settled. So here's a summary slide on the history of computer vision. It's a 50-year-old field, and the early stages were sort of, people just trying out things with very, very limited computational resources. And at that time, it was actually the math was much prettier in the old days because we couldn't just run things on the computer. We had to be clever. So you had to simplify things so that you could work things out, right? There is the cleverness of the theoretical physicist, which is you try to bend the problem by chopping off bits of it such that you can conquer it, okay? And now, okay, you have your huge data, you have your huge computers, okay? Your models are more general and more flexible, but it's the machine which is doing the hard part, not me. So there is a part of me which still sighs for the old days, but it's not the way to solve the problem. The brain is not a cleverly designed entity. The brain is the result of millions of years of evolution. It is not, I mean, God is a hacker, right? As they say. It's a collection of kludges laid on each other. Okay. It's not, the beauty that you have in physics is not the beauty you have in biology. It's a different kind of thing. You have to live with it. Okay. So what can we do? So just what kinds of things can we do in vision? We can now do very good job of 3D reconstruction. I mean, again, the core ideas of this go back to the 80s and 90s. We had these papers back then. Now people can do reconstructions of cities just from images downloaded on the web. The success here is really now what's going to lead to AR and VR. That's really all about this, what we used to call the structure from motion problem. You have multiple views, you determine the positions of the cameras and you reconstruct the world. In the 90s, this was a mathematical exercise. In the 2000s, you had the data to make this work. In 2010, now this is, as it can be done in real time, you get AR and VR. We can reconstruct over time. Now we can use vision to make inferences about the world, tell stories. Okay, we can reconstruct outdoor scenes, we can reconstruct indoor scenes. In fact, I have this image, this is not from my group, but some other group. We can get semantic reconstruction. So not only can we reconstruct the image in terms of 3D geometry, we can also say these are chairs, these are tables, because recognition and reconstruction have both made tremendous headway. I think here's what we should aspire to: model everything in the world. There should be a 3D model of every place, every object. Right? It's doable. There's no fundamental scientific problem left there. It's really engineering, and there has to be somebody who cares. Right? Okay, so I'll try to summarize where we are today by this picture. So you, as a human, look at this picture and what do you see? Okay. So these are some examples of the kinds of inferences you can make. So you can say there's a person walking away carrying 3 bags. There's a person sitting on a bench with a handbag next to her. There's a bench, and then you might match it to a 3D model of a bench. All of this is doable today, at least in sort of prototype research software. We can do this. We can even kind of, there's a visual Turing test for computer vision systems that is being proposed by the Giemans, that we should, I mean, this is not there yet, but it would be. It's a kind of thing you can expect to do in the next few years. Answer arbitrary questions which are, in this box, is there a car? Is there a person? Is that person a man or a woman? Is that person walking or running? Things like that. These are very much in reach. Okay. What's interesting? Okay, so here's the visual system, which, I mean, a lot is known about. The visual system is the most accessible part of the brain, and more is understood about it than about other parts of the brain. Like language areas, we don't know much, because, for example, the language is not there in any animal other than humans. So we can't do electrophysiology, which we can do on monkeys. Right? You can do MRI, fMRI type studies, but they don't give you that same kind of resolution. So I'll tell you some of the more researchy and more interesting problems that there are. I mean, it's not that vision is solved. So a lot of what has been done so far is with feed-forward models of vision. So you have images, and then you have a layer of a neural network which computes something on that, then you compute on top of that, then you compute on top of that. So the information goes forward. In the brain, there are feedback pathways, and we have attentional mechanisms. And if there is some confusing scene, it becomes clear over time. Okay, we want to capture that in our machines. And how do we do that? So this is, to me, an interesting problem. So I'm interested in computer vision tasks where feedback is the key to the solution. So this is going to bring in context and so forth. And this is, a late evening. This is not the time to have equations. So I have only one slide with equations. I hope you don't mind that. Okay, which again I will ignore. But basically, if some of you have done EE degrees, somewhere you must have in your neural networks diagrams of control systems with feedback. So what we are trying to do here is this task of interpreting the human body. Where are the different key points? And once you have a rough interpretation, it enables you to guide the rest of the interpretation. How do you know where is the elbow? It's in the context of the shoulder. But everything is in the context of everything else, so there has to be a chicken and egg problem. So you start with the initial interpretation, which is going to be roughly maybe the head and shoulders, and then it's going to get better. So an example of that is shown in this slide. So these slides show that we start with an initial guess, which is just generic, a person in like this position. And then the network tries to predict how to adjust the positions of the joints. And that's step 1, step 2, and by the time step 4, it has found a pretty good approximation of the human stick figure. So what this shows, and this is the best results on trying to do predictions of where the body, how the body poses are using these kinds of feedback architectures, and we'll see a lot more of those in the future. There's a meta point I want to make, which is that neural networks are just a function approximation device. So you are given lots and lots of input-output pairs, and you want to, your mappings from xi to yi. There is some input xi for which there is an output yi. And I give you lots and lots of examples of xi and yi. And in between, we are going to have multiple layers of a network with some unknown weights. What we are trying to do is, given these we are trying to create this box which can, on the training examples, when you feed it an xi, it produces a yi. It's trying to replicate the performance of those examples, hopefully in a way that generalizes. And that's about it. So it's really just a generalized function approximation device for the mappings which are somewhat continuous and smooth in nature, but they could be very multimodal and so forth. So that's it. So you can, with this, it's sort of as, in a way, as general as thinking about Turing machines. So I think we are now in a new paradigm. We had a paradigm, if you think back to, say, last 200 years of research. Back in the 19th century, physicists had to be really clever. They had to figure out what approximations enabled them to solve the differential equation and create that model. First create a model, then solve the differential equation. Now in the 1950s, computers come along. Now you don't need to have that kind of a simplified model for which you can create an analytical solution. You just simulate it, right? You've got the model has to be good enough so that you can create a simulation. You run the simulation, and for different conditions you can do this. And this revolutionized physics and engineering and so forth. The computer programming, okay? The average computer programmer was obviously less clever than the average physicist of the 19th century, but they could achieve a lot more. Okay, and now we are at the next stage, which is that you don't even have to program the damn machine. You just have to collect xi, yi pairs, okay, and you will have even less understanding than you did with the computer program. But it's going to work even better because it will just replicate the structure of the data. Okay. So how am I doing for time? How much time do I have? 20 more minutes? Okay, that's enough. Yeah. Because I'm rambling, I can quit anytime. So now I'm going to just talk a bit about the kinds of problems we should be working on. What can't we do today? I think computers today have pitiful social intelligence. Okay, we are going to live in a world where there will be computers and humans coexisting. Okay, and the computers. So imagine your robot in the home. Okay, I told you there is a problem there, which is that we need better hands, but that's a side matter. we certainly have the mobility is there, right? So the mobility problems are good. So computers need to understand humans, humans don't need to understand computers. Computers need to understand us, which means that they have to understand state. So when we talk to each other, we understand. So when I talk to you, I know whether you are understanding what I'm saying. Well, maybe I do. I know whether you are angry, whether you're happy, and I modulate what I say in response to that. So computers need to be similarly aware of humans. We're going to be in these environments where there will be many computers and they need this social intelligence. And I don't think we have achieved that. Because going back to this example, there is all that easy stuff. Well, it wasn't easy 10 years ago, but it is easy now. We can say this is a person, this is a bag. But what I really care about is that guy who's looking at that woman. So that woman is clearly a musician. If you look carefully, underneath there is a bag in which there are some dollar bills sticking out. So clearly she is somebody who expects people to tip her because they like her music. And this guy, we don't know. He's trying to decide. And I'm trying to decide, is he a cheapskate? Is he going to listen for 5 minutes and then walk off? Or is he going to go forth and put down a dollar bill? This is really what is important, right? I mean, when you have your robots or AIs in your home, if they can tell you, recognize that there is a person there, that's not a big deal. They need to know your state. They need to make inferences. They need to know what your desires and intentions are. What is your behavior? I mean, this is your conventional, your British butler or the gentleman's gentleman. He knows what you need before you know what you need. So that's what we need. So these are great research problems. So as I said, there are some problems which are now solved or not enough. Not enough is left in them for academic research to really get kicks out of. So for example, we don't know well how to understand actions. So we know how to understand objects, but we don't know how to understand actions well. So here, for example, a scene like this, we need to describe it in terms of so this is where language will come. See, language, as I said, is currently, in a way, it's very successful because obviously mostly how we operate is at a semantic level, so therefore language is the medium by which we will communicate, right? But the biggest successes of language are something like translation systems, which are very effective now. But what are the translation systems? They are kind of like what John Searle tried to ridicule as with his Chinese room argument. They're taking a sequence of symbols in English and spitting out sequence of symbols in French without necessarily understanding what they correspond to. Okay, the typical models are these sequence-to-sequence models with LSTMs. They don't really understand. They will translate the word chair to the corresponding word in French, but they do not know that a chair is made of wood or metal and that people sit on it and it has a certain affordance and the shape of it conforms to the shape of the human body. They do not have any of that. Right? They're just translating a symbol to another symbol. This is not true understanding. In limited domains, of course, we can have dialogue. I mean, Siri pretends to understand us. But language is what we call AI complete. I mean, you cannot properly understand language until you have a proper notion of common sense in all its various forms. And I believe that the key, we won't achieve it until you have solved the so-called, in the cognitive science literature, this is referred to as grounding or embodiment. Grounding is that those words in language, those words have to be associated with physical entity with which you have reacted, which you have touched, which you have manipulated, which you have seen. I mean, there has to be that mapping. Otherwise, they are just symbols, right? So what we can't do, action, we don't do. Action is based on movements and goals, and we can transcribe movements, right? We can compute some pattern or optical flow, and we can classify somebody is running versus jumping, but we don't really understand the goal level well. Classical AI. So this is an example for classical AI. If you are in a restaurant and there's a sequence of events which takes place in some order, and we know when there is an anomaly. For example, if you walk out without paying the bill, how do you know that when you just had a video clip? Well, it's because you take the actors and the events and you match them to some template of what happens in these. That's a proper understanding of what is there in the restaurant. Do our current neural network systems which are translating from English to French have that? No. Okay. Do our vision systems which can recognize chairs and tables and people have that? No. Until you have that, you have not actually achieved understanding. So these are problems we need to work on. I mean, I'm not saying that these are impossible problems. These are all interesting problems to work on, which we will work on. Again, I've said this at various times, but I want to recap. What has been responsible for the recent successes of AI? Big computing and big data. Okay. Actually, there's more to it than that. There's big annotation and big simulation. Because the data, if it was unlabeled, it would not have been of much use. Okay? Humans really manage with unlabeled data, but our machines don't. We really need those million images from ImageNet which have been labeled as, chair, dog, elephant, etc. And big simulation is really behind the successes of DeepMind, which have got a lot of attention, like winning at Go or Atari games and so forth, right? I assume many of you have heard of that. And it sounds very impressive because people think, oh, Go, wow, that's a game which people thought could not be won by humans. But, I mean, the methodology is of so-called reinforcement learning, and for this you need lots and lots of trials, which of course if you have access to big computing you can do. And that's been, and these are scenarios where everything is sort of known, so you can in fact simulate them accurately. Now this is not the way we can expect robots to learn. So these are simulations, right? Games are environments which you can simulate. The real physical world, these are the best learning devices we have today. Okay? How does the baby learn? So the baby learns in the early stages by interacting with the world. Okay, the mother is not going there labeling every object for it. Okay? Nor is the baby doing, a million trials. I mean, it's not. Okay, there are parts of the baby's growth which in fact require a lot of experimentation. So, I mean, here's an example that I've used. There are multiple kinds of learning, of course, but one example is, look, there is a zebra. And you do have those interactions. In fact, formal schooling is all about that. You memorize facts like Paris is the capital of France, right? And this is important, but this is the easy stuff. Okay? Wikipedia has all of these. This is why you had the successes in winning at Jeopardy. But this is, I would argue, is the easy part. Okay? This is semantic knowledge, lists of facts which are very explicitly put. These are what is harder is the stuff. Everything important has been learned by kindergarten, right? It's the stages of learning until you are able to go to school. Once you are at that stage, the cultural transmission of information, which in today's society is done through schools, is actually the easier part. It's much easier to do for computers than for humans, right? Because a list of 100 capitals, a country capital pairs, is trivial for a machine. Okay, but my poor son has to spend time memorizing them, right? So we should keep this in mind. So I'll tell you where I'm going with this. I believe that for the next decade of AI, we really need to develop more general learning techniques. Supervised learning of the type that has been used for these object categories, like learning what's a dog, what's a cat. That's been great. It's behind our current successes. Excellent, bravo. But we need more general learning techniques. And more general learning techniques we will get by, I think a very good source of ideas there is looking at biological and development. So, for example, this example of the kid learning is self-supervision. You don't need to provide a million examples which are labeled. So there is a lot that's known about this from child development. I mean, I think we as engineers and physical scientists think of psychologists as, okay, this is a fluffy field, but it's just that their problems are harder and they will make progress more slowly. I mean, there is this old line, right, that God must have been a physicist. He gave them all the easy problems. I mean, as we go from physics to biology to psychology, the problems are actually getting harder, and that's why we are making slower progress. So, for example, some of the lessons we know, and we are going to convert them into research agendas for computer science and machine learning and so forth. Multimodal. Children are simultaneously getting tactile input as well as visual input as well as sound, and that they provide training signals for each other. There's incrementality, a word, I mean, learning is staged. You learn certain things after certain other things. So the visual system, which at one stage, one example of zebra is enough, that visual system has previously been trained to know how an object, 3D object, generates multiple 2D views. So therefore, from that one view of a zebra, you have a good prediction of how it looks like from different viewpoints. So we don't need to give as many training examples because there is this previous background. Physical, it's not, the brain does not live in a vat. You interact with the world. And vision is not critical to this. Blind children acquire language and full intelligence, but they explore through their touch and through movement. All of that is essential. Be social, use language, and then we have to do work with this. Okay, I think I've gone on too long, right? How much time do you have? If otherwise, I'll show you 5 minutes of the other one. Huh? It's okay? Okay. Yeah. That one. Thank you. Okay, so I'll give you again a flavor of how in my research group we will try to explore these questions. We're trying to take these ideas from child development and trying to operationalize them in sort of computer sciencey ways. So for example, the behavior of a child who learns the world by exploring. So one example is, there is a little experiment that the child has done. The child is like a little physicist, right? He pokes, the Coke bottle falls down, whereas the ball just rolls forward. So the child is a physicist, right? The child is a naive physicist, but in certain ways this is very important. So the child's version of physics, a marble and a feather do in fact behave differently. It was perfectly correct. You got brainwashed when you went to high school that yes, the acceleration is independent of the nature of the object. Because what you've done is, yes, so this more deeper theory that you learned when you started to take physics classes was this has value. I mean, this enables Newton to predict the movement of the planets. So the extrapolation is much greater. But in terms of daily life, what you really want are observations and recording the patterns into something. That's what you need, right? So what the child needs and what AI machines need is not necessarily the fanciest of physics, right? They need to know the behavior of little things in little ways. So there's an idea going back to the 1940s from Kenneth Craig, which is that to operate in the world, we need to have a model of the world. So before I do something, if I have a model of the world, I know what will happen. And some of these models are social models. They are that if I pinch him, he's probably going to cry or he's going to get mad at me. That's a social model. There are physical models of what happens when you poke at an object, or how do you, right? So all of this has to be done. So we need to act in a novel situation, we need models of the agent, models of the environment. And you may have been led to believe that the physicists have solved the problem of modeling the environment, because there is a good first order story, but that doesn't, the physicists are good at sweeping things under the rug. They choose to work on certain problems. They like balls rolling down inclined planes. They don't want to worry about the pattern, if milk spills, what will be the pattern of the string, right? You choose what problems to work on. That's what defines a field, because certain things are easier in that framework. Now, friction, air resistance, these are very important in real life, but we physicists sweep them under the rug for a good reason. I mean, vision, we talk about light. We think that, in a sense, classical optics was well worked out in the 19th century. But still, when you talk about how carpets look and how hair looks, my graphics colleagues have to really struggle at getting hair renderings to be right. It's taken only recently that we can get those things right. Whereas for the physicists, this problem was solved. They've chosen to sweep certain problems under the rug. So what we are doing is, in a way, doing experiments and learning stupid physics, right? Naive intuitive physics. So because that can take into account these other aspects. So we've done work where we are trying to, I won't get into the details, it's way too late. So you can learn the physics of billiards, and then you can use this, you can throw all your neural network machinery on this. We can learn how objects behave, and then from that you can plan action. The important thing is to plan action. We'll give you another example, and I'll kind of stop here. So this is, we are trying to actually simulate how children learn by interacting with the world. So here we're doing these experiments with a robot which is trying to poke at objects. There's a camera which is looking at it. So now we have examples of images where you have the initial image, the final image, both of them are processed through neural networks. There is the action which you commanded, so you know what that is. And now you're trying to look up, you develop these, they are forward and inverse models. So the forward model is, if I perform a certain action on this image, what will be the resulting image? An inverse model is, I want a certain state of affairs, what should I do? And you can kind of train them together and so on and so forth. And again, the details don't matter. I'd like to end here. I think the vision story is important, but it is important in conjunction with all of cognition. Vision, motor control, as well as language. Thank you.
So we have about 15 minutes for Q&A. So we have two people here, Taj on that side and Sasha here. If you can keep your questions brief and one question per person.
Hi. Could you comment a little bit, when we train deep networks, whatever, we collect data and then we train them with backpropagation and then we use them. But we do these in two very, very different phases when we're operating in a computational setting. And of course, in the biological case, these things are somehow coupled and happening at the same time with the same machinery. Do you have any, can you sort of comment a little bit on what you think you or we collectively know about how the biological system works, and if that has any use for us in understanding, like, robots that are things that learn while they're operating?
Yeah, so I think I'll repeat the question. It's really about the style of learning that is done for these neural networks, where there is this initial phase which is training with lots of label data, and then there's test. Whereas a biological organism, or in fact many robot situations, you want online learning. So the term we use is online learning. So you are learning and adapting at the same time. Now, as such, we can do that. I mean, in computer vision systems or robots, that's not a particularly hard problem. I think the bigger challenge is the way in which our style of training these networks differs from what happens in real biological learning, is this requirement of a very large amount of supervised data. So we need to have like a a million examples of which have been labeled. Now, in normal course of growth of intelligence by a child, that is not the case. How many times? I mean, and this is true in many spheres. So there are some things that you teach a child. Okay, maybe you teach the child how to tie her shoelaces. Okay, you do teach them certain things, but mostly they learn by experimentation or by imitation. So they are experimenting, then they are imitating, and then they are fine tuning by sort of practice. And those styles have not been captured well in our machines. So I see that as the biggest problem. Supervised learning, trying to do it in an online way, which is that you have some examples, now you have a system, you can start. So what will happen is that as you have more and more examples, the system will just get better and better. And so that behavior we can show today. So you initially have 100 examples of dogs, and then you add another 100 examples. So after 100 examples of dogs, the system will do a reasonably good job. It will just get better when you have 1,000 examples. But I'm arguing at a more fundamental level that we are missing out certain basic strategies of learning. And maybe we'll figure out how to do that.
I would have a quick question in the context of the so-called next-gen networks that I've heard the name about. Have you an opinion of Numenta HTM, so hierarchical temporary memory, and how this works? It seems to be like in his child stages, but it's been around like 10 years now. So I was on a presentation and I couldn't have a grasp about when that can be used very well. It was mainly emphasized that it's good for anomaly detection, not for visual, as of now.
Yeah, I don't have any specific comments to make on that network. My general approach to this is that in this business, because we can't prove theorems about these, the proof is empirical. So the way I would evaluate different architectures and so forth is that there are certain tasks that people have agreed on, right? So there's some object detection tasks, some speech recognition tasks. So take certain standard tasks on which various people have tried their approaches, and then any new architecture, it should prove itself by coming up with good performance, meaning low error rates on one of the standard tasks. Now usually when people have novel architectures, they say, well, I really designed my architecture for a task which is not one of the standard ones. But then it's difficult for me to judge. I mean, the proof of the pudding is in the eating. That's what, I always take the skeptical attitude. As I said, my response to Hinton 3 years ago was, show me. I mean, you have to show me, and you can't show it on your own peculiar data set. You have to show it on a data set that I would believe.
So, deep learning does one specific task really well. Do you see unsupervised learning changing the architecture of these current networks at all significantly?
Yeah, so the question is about unsupervised learning, and at some broad level, surely we have to figure out how to do unsupervised learning. I find the term, I went through this entire lecture without using the term unsupervised learning, and that was quite conscious, because to me the opposite of supervised learning is not unsupervised learning. It's because there are really many learning modes, and I try to indicate that by my examples of how children learn. I mean, there are modes which involve experimentation. Is that supervised or unsupervised? It is in a way you generating, it's self-supervised, you generate the signal. There is imitation, which is a much weaker form of supervision than the one that we have used for our networks. And so on. So there is actually quite a lot of richness, and the term unsupervised kind of doesn't do justice to that. Unsupervised learning classically became something like clustering or PCA. And those surely are great techniques, but they are far too limited for our goal of building intelligent machines.
Question. A comment, Lisa.
Yeah, Hisam.
the school not only teach children knowledge, but they also teach children to be mindfulness, to walk away from the bully or like resolve conflict, right? Exactly like you said, general learning, which also I want to comment that when Microsoft released their AI figure to do the tweets and blogs, I hope there's no Microsoft people here, and they can only spit out the hated languages because it's very prevalent on the forum, right? So it's not a general learning approach. So my question is like, so the AI now is easy, it's relatively doable for industrial tasks, right? But the whole spectrum from industrial tasks into work life, the full spectrum to the full human being capability, subtleties of emotions, which is God's ultimate creation, right? So what computing power can push us to move the needle, right? So just by huge sheer force of GPU and computing power, the learning, the general learning, we will need more. What's the breakthrough?
So my general feeling is at this point we are not really compute bound. We used to be. I think the past history we were compute bound. I think right now we are idea bound. We need more ideas. I mean, right now we are living off, some of the big successes are of ideas which are actually quite old. They've just been carried along by the power of computing and data. But this is not where it ends, right? We are on the journey towards full human level intelligence, as you eloquently pointed out what's not there. I think it really needs new ideas, new learning architectures, okay, new ways of approaching the problem. So the frontier of research is actually quite open. And a lot of this is not going to lead to anything practically useful in the near future. For practically useful things, best thing to do is in fact to stick with supervised learning, try to find a good data set or find a way to create the right kind of data set and work with it, or reinforcement learning in certain settings. So today that's the way to go if you want, often there are many practical problems which can be coerced to fit that paradigm. But I'm saying there is more to work on, and I as an academic researcher want to pursue that.
One thing that you mentioned that is still not done is language, semantic reasoning, knowledge graphs. But those things also have been tried for a while. Syke and Doug Leonard, when they started back in the 80s. So what's holding us back there?
Okay.
Is it not enough data or?
A good question. So his question is about language and knowledge, that there are classical AI tackle these problems. But classical AI took symbols as given. So symbols were atoms, right? So they would have properties of something, but those were treated as symbols and in some logical framework. So what was wrong with that style? I think one was there wasn't a proper treatment of uncertainty. So they used logic frameworks rather than probabilistic frameworks. Because what Syke was about was encoding facts from Encyclopedia Britannica. But the facts were essentially like logic formulas. Whereas a lot of human knowledge is probabilistic in nature. And that was not captured. And the second was lack of embodiment. The symbols ultimately have to be grounded in the physical world, which we perceive and which we manipulate. I think that we kind of need to have both those. Now we can do it much better. I think both of those areas have advanced much more than the state of the art in the mid-90s. Now what we have neglected in this current paradigm is we have neglected symbolic reasoning. We have neglected the kind of stuff that those folks used to do in the 80s. It is time to bring it back, but how do you layer it in a certain way? One is a discrete world, one is a continuous world. It's sort of a challenge to figure out how to put it together. And we have to do it.
Professor, first of all, thank you very much for your talk. I think after today, I'll respect my hand more than my brain.
Yes.
I had a very quick question. So, deep learning is doing great, so it seems to be working fine. But not many people actually know that why it is working so well. So let's say I start with some combination layer and I add one more layer on top of it, change the activation function and keep that working. Maybe I reduce the error rate by some percentage. But I don't really know why that happens. So do you think any research would start in your term where we should aim understanding that, okay, using what activation function would work, using how many layers would be better, or why it is working and how it is working?
Yeah, no. So his question is about research on understanding networks better. No, this is an active field. I mean, I think that people are trying to do this. It's just that they're not having that much luck. I mean, I mean, we have good rules of thumb. There is an empirical, the art is somewhat understood. I mean, the reason why some of this neural network stuff took off is because different people could replicate it. So it's gradient descent, which finds local minima. But the fact is that I can train a network in my lab at Berkeley, and somebody can train their network in Stanford, and somebody can do it in Google, and they will be different networks, but they will perform somewhat comparable if the architecture is somewhat comparable. So that is interesting, and this is the robustness which led to the explosion of this field. Now, why is it that we don't get stuck in bad local minima? So there are theories on this, right? That it's to do with the properties of high dimensional spaces and so on. And people are exploring this, and there are some little theoretical results here and there, but they're not powerful enough. But empirically it is solid. I would appeal to you to the history of medicine. Medicine for many years, I mean, when did these guys know about genes and DNA? It's in the 1950s. But medicine worked quite well before 1950s. Antibiotics had been invented, right? So you do not have to understand the system to be able to manipulate it. And medicine is a prime example of that. It's a very empirical field. It has become more and more based on biology and science, but it was not so. And even now, lots of things are just empirical. So learn to embrace it.
Question. So maybe along the same lines, so if the neural network is a brain, right? You have all the intermediate states of those layers. I'm talking about the deep network. So do you see a value in opening this black box and seeing what's happening inside? Do you think this will?
Yeah, we do that. I mean, when we do research, we are trying to make sense of the receptive field of the neurons. There are people developing, publishing papers on visualization techniques. If you go to, the proceedings of something like NIPS or CVPR, there are lots of papers on neural networks and so on, and some of them are about trying to visualize and make sense of what the neurons are doing.
Yeah, do you think that the intermediate neurons carry some important information not in the outside layer?
Yeah, in vision they are often about parts. So they will correspond to parts, whereas the highest layer will be more about full objects.
Jitendra, can you explain what combination of deep learning and wide learning means, where deep learning is about generalization and wide learning is about memorization?
Deep learning and what's the other term?
Wide learning.
Wide.
Wide, W-I-D, okay. Sounds like a good term. How can I be opposed to it? So everything is needed. I think that in AI we have had these times when somebody pushes just one paradigm, and I think that we need multiple paradigms. So I'm fine with that. I don't have anything to contribute to it. So.
Okay. Let's take two more questions. Go ahead.
So I have actually two daughters, and here. So I have two daughters, and they're about 7 years, 6 years apart. I noticed the elder one growing, she was good at these memory games and things like that, and you had the same game. The younger one was also playing that. What I noticed is the younger one was very good at retaining those cards. I mean, you just flip it and they're able to retain it, right? Recall the thing. And the elder one was not able to recall after a few years. So I got very interested and I actually have a video recording of the younger one flipping these cards, and it looks pretty random, and then in one shot she's able to get 16 of them flipped over. I went and talked to a neuroscientist, I showed him actually, and what he told me was in the first 2-3 years when the child's brain is developing, it actually just grasps things without any context. I mean, it's just learning things. But after like the 5th, 6th year, its retention starts to get down because it starts to associate context with it. Now the second part is, we know that like vision, like if you go blind, there are certain neurons actually get retrained and it is used for hearing. And then there's the third part, which is Asperger's, where there are these high functioning things. So the raw material is the same, but they're thinking in some different way, which we don't know. So my question to you is our understanding of the neuron also like is complete, or there's some different ways in which
the brain is the final frontier, right? So scientific understanding of the brain, there is not more to do. I think theirs is the harder problem. We might build artificial machines which are quite effective and useful long before we understand the human brain.
Here, we have the last
One last question. Go ahead.
Professor Malik, thanks for the great talk. It's really thought-provoking. To me, currently, I think the learning techniques in some way goes hand in hand with how the learning experience is stored and represented. So,
sorry, could you speak a bit louder?
Oh, I think currently the learning techniques goes hand in hand with the learning experience and the knowledge how it's stored. I just wonder if there's any value or if there's any research on having a generic knowledge representation framework or format, so this information can be generically used for retrieval, reasoning, problem solving, or if you see there's any value in doing such kind of research.
No, so there are people who work on general knowledge representation, knowledge graph, things like that. So there's sort of the people who are into the semantic web. So there is an area of research which comes from kind of more traditional AI type techniques where you develop ontologies and you have, so certain kind of knowledge is best represented like that. So Paris is the capital of France, right? You have to represent it in this kind of a symbolic framework. To me, the interesting challenge is the kinds of things we do with deep learning and then the kinds of things we can do with this more classical framework. They are right now complementary. How do they work together? Because in this brain, they work together, right? Because classical AI suffers from brittleness, right? I mean, we used to use classical AI techniques for robotics, and then you have a primitive, and if it doesn't do what it does, your whole thing breaks down, right? Or you define a dog as, okay, it has 4 legs and this kind of, and you write down the description which you try to implement as a computer program. It's very brittle, okay? The learning-based approaches are much more robust. But there is symbolic reasoning and there is language, and we need to, I mean, we certainly do it, so we need to do both.
Great. Thank you for this great talk. Some of you I know have questions. So, thank you.